Okay, so got a bunch of announcements for today. First one is if you haven't done your SCQs online, I think the deadline closes in a few days. I want to say Monday or Wednesday next week. So please do those. I guess like they don't show me any responses yet, but they do show me the response rate, and I think we're about like 28% last I checked. So please, like any feedback that you have, I'm happy to hear it. And then Saplings, Chapter 23 is due Wednesday 9 a.m. And then turns out it is okay to have homework due like online after that. So I'm just setting the due date for Sapling Chapter 24 at the start of the final. And then the final itself is Wednesday, finals week, 7:30 a.m. in Math 100. And I did manage to set up the details for the exam review session. Turns out they didn't have anything big enough later in the day that also has lecture captures, so I had to push it back to 10:30 a.m., which I know like a few people had problems with time-wise, so sorry about that. That's what we could grab. So I am setting up lecture capture in there so that if you can't make it, you can still watch at least. Quick show of hands, like how many people want to come to the 10:30 a.m. session but won't be able to time-wise? Oh man, okay, well, sorry about that. All right. Okay, so any questions about this stuff? Oh, yeah? No, it's actually Dwayne G130, so they didn't give me like the huge room that's downstairs. It's like up a floor from there. So I don't know how, I think like it's at least 100 people, which is more than have been going to the midterm exam reviews, but yeah, the huge ones were all taken for exams, unfortunately, yeah. So, okay. Any other questions about this? Okay, cool. Alrighty, so we wrapped up chapter 23 last time, which was the last functional group specific chapter that we're going to look at. So now what we're getting into, this last chapter is a little bit of an intro to biochemistry. So actually, show of hands, like how many people are going on to take two semester biochem sequence from here? Or intro to bio, or the one semester one too. Okay, nice, so a ton of you guys. So this is going to show up some in biochem. I guess like the way it's framed in Loudon is like sort of a crossover, like they're still a little bit more organic specific and they don't get like super far into biochem kind of level of detail, but it's kind of a good like lead in, I guess, to tie this course into the next one. Okay. So chapter 24 is carbohydrates. Okay. So carbohydrates are a fairly ubiquitous class of compounds. They show up a ton of places in biochem. And the general sort of descriptor for everything in this class is anything with a formula of CN, H2N, ON. N can be any integer. But if you reorganize that and sort of group together units of H2O, you get CN H2O N. which is kind of where the name comes from. They're a hydrate of carbon is how you can look at it. It's like some amount of carbon plus the same amount of water molecules. Okay, so this is a very common formula for sugars and things derived from sugars. Okay, what kind of degree of unsaturation does this formula have? Just to suddenly throw you guys a pop quiz. Yep, yeah, it's got 1 degree of unsaturation. Which we know because you can drop all the oxygens out of the formula, and then you end up with CnH2n. If it were saturated, you'd have CnH2n plus 2, or missing 1 pair of H's. That's 1 degree of unsat. So 1 degree of unsaturation. So how the structure for these things normally looks is a chain of carbons, dang it, where each carbon along the chain has an OH group and an H coming off of it. And then to get your 1 degree of unsaturation in there, one of the carbons has a carbonyl on it. Okay, so sort of a general, like no stereochem indicated structure way to draw this might be, so here's a 1, 2, 3, 4, 5, 6 carbon chain. And so like every carbon along the chain is going to have an OH. And then somewhere along the chain, you're going to have a carbonyl. And if you want, you can also fill in the H's coming off of each carbon, but you don't have to. Okay, or for example, you might also have maybe a chain like 1, 2, 3, 4, 5, 6. Let me actually do a slightly different example from what's in the notes, just so I can get some comparison. So this also fits that pattern. It's a chain of 5 carbons where, again, each carbon has an OH, and one of them's got a carbonyl on it. Okay, so we can actually categorize these a little bit by, first of all, how many carbons are in the chain, and then second of all, what type of carbonyl we have. So this one has 6 carbons. We're going to call this a hex, and then pretty much every compound in this chapter ends with ose. Like all of the sugars that we're going to see end with ose most of the time if they're following this hydrocarbon formula. So this is a hexose because it's got 6 carbons. This is a 1, 2, 3, 4, 5. This is a pentose. We can also describe them by what type of carbonyl we have. So this is an aldehyde. Which means that we can also describe this as an aldose. This is a ketone. So we're going to describe it as a ketose. So pretty much take whatever parent chain name or functional group, throw ose on the end, and you're probably not going to be wrong about naming this. And we can also combine these. So this molecule is both a hexose and an aldose. It is an aldohexose. And this is a ketopentose. Okay. All right, so each of these is a carbohydrate. It's also called a saccharide. And because they just have a single unit of this sort of carbohydrate formula, like an alkyl chain with some O's coming off of it, they're just a single example of a saccharide. So these are both monosaccharides. You might notice this part of the name is actually where the artificial sweetener saccharin comes from. And saccharin also means like cloyingly sweet in general. So all of these things are sugars. They taste sweet to varying degrees, but they're all just like single sugar chains. They're both monosaccharides, and we're going to see later on that we can combine these into long chains of what are called polysaccharides. And if you want to be specific about how many repeat units, you can have like disaccharides, trisaccharides. So like table sugar is a disaccharide. It's two different ones of these things linked together in a specific way. And starch and cellulose are both long polysaccharide chains that are hooked together in two different ways. Okay. So questions about that so far? Okay, cool. So before we get into it, so I was deliberately very vague about stereochemistry when I drew these. Turns out pretty much every carbon along the chain for these things is going to be an asymmetric carbon, because every carbon with an H and an OH is, unless it's like in the middle of a symmetrical chain, is going to be having 4 different groups coming off of it. So these are very stereochemically rich, and we need some good way of like keeping track of their stereochem in a consistent way. So you may remember from one lab that you did in OChem 1 where we introduced Fischer projections briefly. Those are going to show up here. Yeah. So in the lab, we sort of have to introduce that a little bit early so we can talk about erythro versus 3O, because that's how the melting points are listed. But now we're going to sort of get into it in a little bit more detail. So these are just sort of a formalized way to keep track of stereochem consistently. You can show everything with bold and dashed if you want, just there's so many different ways to draw the parent chain with different zigzags and like rotated around and whatever, that like converting back and forth between them is kind of a pain. So Fischer projections like are a little bit easier because there's generally only 1 or 2 like correct ways to show a Fischer projection. Okay, so starting with something with just a single asymmetric carbon, I'm going to call them A, B, C, and D coming off of there. The way you want to think about this is we want to redraw this as sort of a plus shape, where the 2 that we show vertically are both pointing slightly away from us, and the 2 that we show horizontally are both coming out towards us. So we want to have like our single carbon in the middle have something going up and away from us, and down and away. And then the 2 coming out to the side are always coming slightly out towards you. So we don't have any particular way that we have to orient this molecule. There's like no rest of the chain we have to worry about. So I'm just going to draw my eyeball sort of down here, looking sort of up at this. Let me scoot D out of the way a little bit. So sort of looking up at this so that C and D are coming out towards me, and then A and B are sort of vertically going away from me. So that's going to look like A, B, and then C is coming out towards me. It looks like it's going out to the left from my eyeball's point of view. And then D is also coming out towards me to the right. Okay, so this is still tetrahedral. We don't have any bonds that are shown in plane anymore. So like 2 are bold, 2 are dashed, but that's still sort of a tetrahedral arrangement. So what Fischer did was take this kind of tetrahedral drawing and then take out the stereochemistry and just have it be implied by position. So the Fischer projection is actually just going to be this, where C and D, because they're horizontal, are implied to be towards us. And then A and B, because they're vertical, they're implied to be going away from you. Okay. So if we do this on a bigger molecule, say something like so I'm going to draw a different one where it's now a 4-carbon parent chain, and you can think of this as sort of like a bridge that's arcing out of the paper towards you. So like methyl's down, and then these 2 central carbons are both sort of like flat against the plane, and then this other methyl is also in back here. If I have groups like A, B, C, D, then I can draw the Fischer projection of this as just everything looks like it's drawn with in-plane bonds, but we know because of the positioning that A and B and C and D are all implied to be sticking out towards me, and then the backbone is sort of doing this like archy bridge thing out of the plane of the paper. Or alternatively, these 2 are flat in the plane, and then the 2 methyls are in back. Okay, so questions about that one? Oh, yeah?
Which carbon are you looking at to make that Fischer projection? How would you
Good question. I guess like if I were looking at this from, say, the side, and I'll do a couple examples of like more complicated molecules later on, but so hopping over to here, I guess like I would see this as, so here's sort of the bridge shape of like my eyeball seeing it from the side, and then B is coming out towards me off of what is now the right carbon as my eyeball's looking at it, and A is going away from there, and then C is sort of going away from me on the left carbon, and D is coming towards me out of there. So is anyone having a hard time seeing that? Like, I didn't bring my giant model kit, but like if you're having a hard time visualizing these, like with anything stereochem related, definitely play around with models for a bit, and like being able to pick the thing up and rotate it around might make a big difference. So, okay. All right, so let's do this with a longer actual molecule and see how that goes in terms of converting to Fischer projection. So I guess actually let me draw a little box about that first. So converting regular zigzag or skeletal structure to Fischer. What you want to do is, so because of the implication that like every bond along the backbone vertically is curving away from you, that means that we're going to have to take the main parent chain of the molecule and curl it up into sort of a C shape, or like a curled up shape. So like basically every bond or every angle along the backbone is curling in the same direction. So we're going to curl up the backbone, and then we're going to look at it from the side. Okay. Okay, and just as kind of a side note here, just because we're sort of formally twisting the molecule into this shape so that we can draw it in a standardized way, doesn't mean that has any bearing on what the molecule itself is actually doing in reality. Like curling up into a C shape might be like not great as far as like gauche-butane interactions or whatever, but it's just sort of a way of like pinning it out in a very rigorous way that we can easily compare between other molecules. Okay, so let's do this example. Okay, so we got stereocenters on 4 different carbons along the backbone. All right, so what we're going to do first is sort of take this backbone and twist it so that every bend along it is curling in the same direction. You can have it either going like clockwise from the left or counterclockwise, and it doesn't matter too much. I'm just going to turn this into like so that it curls up counterclockwise starting at the phenyl ring. So what I'm going to do is, all right, so this angle here, the first one with the bromine on it, is already pointing in the right direction if I want to go counterclockwise. So I'm going to leave that one as is. Let me actually draw the backbone first. Okay, so 1, 2, 3, 4, and then the COH. So 1, 2, 3, 4, and then COH. Okay, so that's what I'm going for here. So basically, this one with the bromine on it is already sort of kinking in the right direction. So I'm going to leave that one as is. This one here with the OH and the CH3 on it is bending in the wrong direction for how I'm trying to get it lined up. So what you can imagine doing is like if I have a model kit where I've like laid this thing against the board, what I'm going to do is grab this one carbon of the chain and sort of like holding everything in place, I'm going to grab this one carbon out and sort of rotate it around so that it basically does a 180 while the other stuff it's connected to more or less stays in place. So this OH that's coming out towards me rotates like up and over and ends up sort of pointing down and into the board. Is anyone having a hard time seeing that, or does,
So with the projection, which bond, can you just like tell me which bond you're like trying to look down?
So it's not a single bond anymore. It's sort of like you're imagining viewing this thing from like the outside of the curve, I guess. And so your eyeball might end up having to like move around as you're drawing different parts of the Fischer projection. So it's sort of like if you get it curled up this way, then like you're sort of showing it as if like the stuff coming off this carbon is pointing out towards you if it's on the outside of the curve. And meanwhile also up here like this stuff is pointing out towards you since it's on the outside of the curve. So really your eyeball isn't like staying put the whole time like it is for Newman. It's just like I guess all the horizontal groups need to be coming towards you, but when your eyeball is on the outside of the curve, there's a bunch of places it could be and still have stuff coming towards you. So yeah. Uh-huh.
So instead of visualizing the like thing coming out of the board,
Mhm.
would it work to just if you mess with the angle, you switch the stereo?
Exactly, yeah. Yeah, so that's another way to do it where if you have to take this carbon and like flip it to something where it's bending the other direction than what it's shown currently, then you pretty much just flip what's bold and dashed. So this one is going to end up sort of rotating around, so OH is dashed and CH3 is bold. So, and actually like that brings me to another thing that's sort of an easy way to do this. So these two carbons are already bending in the right direction, so we're going to keep those the same. While these two carbons, we're going to have to sort of flip them over to get the bends going in the right direction. So pretty much every other carbon stays the same, and then every other carbon in between those is going to flip bold and dashed. Okay, so even if you can't visualize it, you can still sort of follow the pattern of like like every other one stays the same, and then the ones in between swap stereochem. Or swap, what's shown bold and dashed. Really, they're keeping their same stereochem. Okay, so moving along, chlorine's bold here, and then bromine is going to have to be bold there.
What was that about? Like if you rotate it, switch the stereo?
Mm-hmm.
Can you rotate like the blue to the top? So why don't you do
So this carbon is actually already like bending, like as we go along the chain, it's already bending me counterclockwise, which is how I sort of set up this one to be. And so, yeah, so I'm just sort of like trying to go, like if you follow the direction of the chain, this one's sort of going this direction. So if you're like looking at how you go from starting at the phenyl as you traverse along the chain, like this one is going counterclockwise, 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 and counterclockwise. No, you actually have free choice of which way you can show it. So I'm just sort of arbitrarily picking this one, and I'm also arbitrarily choosing to start counting from the phenyl ring. You could also view it as if I start at the carboxylic acid, then everything's going clockwise from there. Really, I just got to be consistent. As long as I do that, then it works out okay. So just to compare that to over here, here you're going clockwise, here you're going clockwise, but at these two that I flip, the chain is progressing like, sorry, here I'm going counterclockwise, counterclockwise, but at the two that I had to flip, I ended up going clockwise as the chain bends, and so that's why I have to sort of pull those out of plane and rotate them around to get the right direction of twist. Okay, so a few different ways of like how to remember how to do this. Hopefully at least one of them clicks for you guys. If not, I definitely recommend like building a model of this particular one or whatever you want, and then just sort of playing around with it so you can get it to this curled up shape of the backbone. Okay, so questions about that? Okay, yeah,
So now
that's it.
like the backbone skeleton,
The Fischer projection? Yeah, I'll do that one real quick first, yeah. Okay, so now what we're going to do is look down at this from the outside of the curl. So I'm going to just arbitrarily choose to put, I guess by convention we usually put the most oxidized carbon at the top, but really it would still be a fine Fischer projection if we didn't do that. So I'm just going to go COOH up here, and then I have 1, 2, 3, 4 asymmetric carbons going along. So 1, 2, 3, 4, and then at the bottom now I've got the phenyl ring. Okay, so what I want to do is sort of like scan my eyeball around like the outside of the curve. So looking down on like here from above, bromine is coming out towards me, and it's going out to the left from my eyeball's point of view. Does everyone see that okay? Like, okay, good. So I've got bromine sort of sticking out on the left, and then on the right, what do I have? H, yeah. So if I'm not showing anything in zigzag, it's implied to be an H there. Next one down, I got chlorine, and again, I can like adjust my eyeball's position so that I'm sort of viewing it from where I'm actually like directly outside of the curve. But chlorine is again coming out towards me, and then H is going, chlorine's out and to the left, H is out and to the right. Next one, CH3 is out and to the left, OH is out and to the right. And then next one, bromine's out to the left, H is out to the right. Okay, so once you've got it sort of drawn out this way, then you just sort of have to like go along carbon by carbon and show what's attached to the left or to the right. But switching it to this is usually kind of the harder part. Okay, so questions? Yeah. Let's see. Like here versus here? Yeah, then it would be sort of like if I had the bromine dashed on here, then bromine would be on the right and H would be on the left, yeah. Okay, so any other questions about how I'm doing this? Yeah?
What happens if you look at the first bromine to the other side?
Mm-hmm.
Would that change, like she asked, would that change what side it's on the Fischer projection? So say you like looked at it from the left instead of the right, would that change what side it's on?
Oh, so in other words, like if I flip this upside down so that phenyl was up here, like, so I was sort of like looking at this, so like, sorry, I think this is what you're asking, but, so if I looked at it so that bromine was on the right here, then phenyl would be up. And then H would be left. And then as I go along, like, yeah, CH3 would be out and right. OH would be out and left. Here, chlorine would be out and right. H would be out and left, and then bromine and H. Okay, yeah, so that's actually a totally valid way to draw this as well. And you'll note that pretty much you can take a Fischer projection and turn it 180 degrees upside down and get the same molecule. So flipping Fischer 180 is same thing. Yeah, so I could draw this either way up and still have it be a fine Fischer projection. By convention, we put the most oxidized carbon at the top, but yeah, it's still like a valid way to draw it. Okay, other questions about that? Okay, cool. All right, so these are very stereochemically rich molecules. So we know that every asymmetric carbon can be either R or S. So a molecule with N stereocenters and by the way, this isn't the same N that we used in the formula of CnH2n plus ON. It's just a separate whatever integer we want it to be. So with N stereocenters, there's going to be 2 to the N possible stereoisomers. And so for something with only like 3 or 4 stereocenters, we're already getting into sort of an exponential increase in the number of possible isomers. So drawing up our aldohexose again. So pretty much every carbon along the chain, except for the 2 ends usually, is going to be a stereocenter. I guess the 2 ends plus the carbonyl, but if the carbonyl is one of the ends, then that kind of overlaps. But pretty much like every carbon except a few of them is going to be a stereocenter. So this has 4 stereocenters, so 16 possible stereoisomers. Or if we do something that's a ketose, then again, everything except the 2 ends and the carbonyl is a stereocenter. So here it's got 2 to the 3, or 8 stereoisomers. Okay. So this is kind of why Fischer projection is useful. It's a good way to keep track sort of formally of how exactly the stereochemistry is laid out in our molecule. So the way that we're going to subdivide these is, I guess like we know out of the 16 or 8 or however many stereoisomers, they're going to be split up into pairs of enantiomers. Where every stereocenter is flipped between those 2 enantiomers because those are mirror images of each other. And so we need a formalized way of keeping track of how to describe sort of the relationship between 2 enantiomers. So out of the pair, both are going to have the same name. But one has D at the start of the name, and one has L. And the way to tell between them is if you look at the stereocenter furthest from the carbonyl, the stereocenter that's normally shown at the bottom, If the OH there points left, is an L sugar, or an L molecule. If the OH is on the right, it's D. Okay, so as a couple of examples here. All right, so here's Fischer projection of an actual carbohydrate. It's got, this one happens to be an aldohexose, so it's 6 carbons, 1, 2, 3, 4, 5, and then 6. It's an aldose, so we have this carbonyl at the top, and then the bottom carbon is not actually a stereocenter because it's the end of the chain. So if I show kind of arbitrarily left, right, right, right for my OHs, so like OH over there on the left, then right, 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 and then I just fill in H's everywhere else. So this is going to be the enantiomer of the mirror image, so it's now right, left, left, left for my OHs. Okay, so these two are enantiomers. Like always for enantiomers, we'd expect identical physical properties, but they might interact differently with chiral systems, aka everything in your body pretty much, because biochem is pretty much all about chirality. So these two happen to be both called altrose. We won't like really go into the names of like how to name different hexoses, but they cover in the book like all of the possible structures of these. But this one, we look at the lowest stereocenter furthest from the carbonyl. OH is on the right, so it's the D form of altrose. This one, OH is on the left, so this one's called L-altrose. Okay. So generally, D sugars are sort of the ones found most commonly in nature, but you'll occasionally see like L sugars pop up as sort of like the unnatural enantiomer, or sometimes like stuff will synthesize it, but not as frequently. Okay, so one other thing regarding stereochemistry is, so these two are enantiomers, everything's flipped, but any molecules that are almost identical, actually, well, here, for that. But they have just one stereocenter different. Are called epimers. So those are not enantiomers. Those are not going to be mirror images of each other. And so those are actually just one of many of the possible pairs of diastereomers out of this set of 16. So if you remember, like pretty much every possible other combo of the 16 possible isomers, other than the pairs of enantiomers, like every other relationship within the set is going to be some stereocenters are flipped, some stay the same, so they're diastereomers. But some of them are closer to each other than others. Like if you only have the one stereocenter difference between two forms, then they're epimers and they're almost the same, but that ends up affecting their physical properties, so you can still tell them apart. Okay. Questions about those? Okay, cool. So, so far we're keeping all these things in sort of like pinned out Fischer projection form, but it turns out chemically they're not always going to be doing that in reality. How much time I got? Okay, like 6 minutes. So you'll notice that we have a ketone or an aldehyde in these molecules, and we also have an alcohol, or a lot of alcohol groups. we know that those particular functional groups can form hemiacetals and acetals together. So we're going to look at these things cyclizing onto themselves. So we can form both acetals and hemiacetals. For the time being, with the molecule just like in isolation and not reacting with anything else, we're going to focus on hemiacetals, and we'll get to acetals later. And we actually have a bunch of different OH groups to choose from along the chain. But like always, 5 and 6 membered rings are the best. So the molecule is probably going to pick an OH group that gives it either a 5 or a 6 membered ring. And so we might have to show it both possible cyclized forms, depending on which one it happens to choose at that time. Okay, so so it can either form a 5-membered ring, which is called a furanose form, because if you remember, furan looks like this. It might also jog your memory that tetrahydrofuran, or THF, looks like this. So this is kind of, we're going to form a 5-membered ring where it's 4 carbons and an oxygen. Or we can form 6-membered ring, which is called the pyranose form. And like always, we're taking the name of some compound and throwing an ose at the end and being like, yep, that's a sugar. So pyran, or pyran, is a 6-membered ring with an oxygen in it. Okay, so let's practice making one of these. I'm going to draw, I guess L-altros is the one that I have in the notes. Okay, so I've got OHs on the right, left, left, left. So if I want to form a 6-membered ring here, I'm going to have to include 5 carbons and then the OH. So I'm going to start at the aldehyde. It's carbons 1, 2, 3, 4, and then 5. And then the 6th atom that closes the ring and cyclizes back onto the carbonyl is going to be this particular OH here. So what I'm going to do is I'm going to sort of gloss over the mechanism, but it's the same old mechanism for either acid or base catalyzed hemiacetal formation. But assuming that we either protonate this or deprotonate this, I'm just going to show this coming in, kicking up the carbonyl here, and being very vague about stereochemistry for the time being, I'm going to be forming a ring where I've got this going on, so carbons 1, 2, 3, 4, and 5. 5 is the one where the OH actually comes around and closes the gap, or closes the ring. But then 5 also has this CH2OH hanging off of it, like that. And I can tell which one used to be the carbonyl because its oxidation state is still the same start to finish, just like it is for making a regular hemiacetal. I start with 2 bonds to O here at carbon 1, and I end with 2 bonds to O here, and this is the only carbon in the molecule where that's true. Carbon number 1 must have been the carbonyl to start out with. Okay, So I did not show any stereochemistry on here because we have a whole additional pattern of making formalized stereochem there called Haworth projections. But I don't think I have enough time to get into that, so I will do that next time.